There's Harry Bear right there. Okay, so he's going to help me with this lesson. Put him right over there in the corner. And let's put a title on this. Classifying chemical reactions. So scientists use models all the time. And so I'm going to be showing you some models. And I'm just going to, instead of say I had, let's do an example reaction. Say the Martian reaction. I really love that one because this is something that it goes forwards and backwards, and we can. It's something that you readily understand. Let's take the Martian reaction, not the decomposition of water, but the synthesis of water, where we take hydrogen gas. So hydrogen's diatomic, and I'm telling you here with the little g that it's in the gas form. And oxygen gas, oxygen likewise is diatomic, so there's always two of them found in nature and as a gas. And when we combine them, we are actually going to synthesize H2O. Okay, so hydrogen gas and oxygen gas combine to form liquid water. That is what the Martian did. So liquid water, I'll put that as a little L in subscript. Now, I think I'm going to make a separate video about this because the questions come up. What are these little things, these subscripts that I've put in here? Well, there's gas, and there's liquid, and there's solid. This just basically tells you the state of matter. So whatever you observe the reactants are, you would put that as a state of matter in these little subscripts in parentheses. Okay, so I was talking about models. Now I want to model this reaction using just letters. So this model is going to be like generic. So it could be hydrogen or something else that I'm putting together to form some new compound. There's a whole class of reactions, and these are called the synthesis reactions. All right. So in general, if you have one thing and you combine it with another, then you will get a compound formed with those. So this is basically A plus B is going to produce AB. This is a synthesis reaction. You take two things and you put them together to form a compound. Okay, so this is my model. It's generically speaking, so my A is not supposed to be like some sort of element A or some sort of element B, because you're not going to find, well, you're going to find B on the periodic table, but I don't think A is on the periodic table. These are letters. They're just, in general, they're standing, A in this case stands for the hydrogen gas, and B in this case stands for the oxygen gas, and AB stands for the compound formed by those two elements. So you get what I'm saying when I say model? Okay, so let's, that is one type of reaction and the model and an example. So I'm going to write that back up here. Anytime you see an A plus B yields AB, we're going to call that a synthesis reaction. Okay, now there is like the opposite of that one is the decomposition reaction, where you have some compound and then something happens and you break it up. Okay, so you break it up into its components, A plus B, and this is called a decomposition reaction. Okay, so an example of that, we talked about hydrogen peroxide, which is in the brown bottles in your medicine cabinet. And it's brown because if you expose it to light, I'm going to draw a little lightning bolt. If you expose it to light, then that actually breaks the hydrogen peroxide down into liquid water and oxygen gas. So that's kind of the reverse of making water. This is taking this hydrogen peroxide has broken this down. Okay, so that's an example of a decomposition reaction. Now, what about the dance? Mr. A was talking about the dance. I mean, so far, all that I've showed you, you could have seen in all the other videos, but I don't know that any other instructional video that you've seen has talked about the dance. So what do I mean by that? Well, take, for example, in this reaction, where someone goes alone to the dance and someone else goes alone to the dance, and then at the dance, what happens? Anyone? What's this look like happened at the dance?
They got together.
Yeah, they hooked up. Thank you very much. So yeah, you all feel free to jump in here. It makes it more fun because it's going to get a little bit more interesting at the dance. All right, so in this next reaction, a couple goes together, and what happens at the dance?
They split up.
Yeah,
They break up because maybe, one person stepped on the other person's toes during the slow dance or some major social faux pas like that, right? So, yeah, we got to keep it together here. All right, so now I'm going to show you another type of reaction. Say A goes to the dance alone, and B and C are at the dance. And then something happens at the dance, and A and C leave the dance together, and B goes home alone. What happened?
Somebody stole somebody's significant other.
You could be something like that, right? There's all sorts of patent place kinds of things that could be going on. Or maybe just A was a little bit better looking, a little bit more attractive, and C said, okay, B, you're a loser. I'm hooking up with A, and goes home like that, right? So we would call that it's actually called, the formal name for that is called a single replacement, right? Am I running out of space? Squeeze it in there. All right, single replacement reaction. Okay, because one couple got replaced by this other person. Okay. All right, and well, not finally, because there's actually 5 major classifications. Really, only 4. Let me talk about that in just a second. This next one. AB and CD go to the dance. AB's a couple and CD's a couple. Now watch what happens. Let's see, this is a metal and this is a non-metal, this is a non-metal and this is a metal. So we're going to go AD. So the metal has to hook up with a non-metal, and this is not saying anything about sexual preference. This is talking about metals and non-metals. This is B, and C is the metal. It comes first, right? So then, all right, so CB. Okay, I have to get this straight. All right, I have to draw my little lines there to make sure I get it right. Okay, so AB and CD go to the dance, but AD and CB leave the dance. What do you call that?
C and B don't really like dances, so they just left, and A and D are party people.
Could be. There's also a word you may not have heard, swingers. Swingers,
Yeah,
you ever heard of
I
that?
didn't know. Okay, I didn't know about school appropriate.
Well, this is for educational purposes only, right? Right. So it's a partner swap, right? So they switch places, right? And that's why it's called a double replacement reaction. As there's a lot going on there, and the only thing you got to keep straight is look over here, and the position of the elements it tells you how you need to follow through. So if A comes first, A has to come first over here. If C comes first over here, C has to come first over here, because A and C are the metals, and then B and D are the non-metals if it's some sort of a binary ionic compounds that we're talking about. Okay, and then the last reaction that I want to talk about is any old hydrocarbon burned in the place of oxygen is going to produce CO2 and H2O. Okay, this is called the combustion reaction. Doesn't have anything to do with the dance, except for the fact that a combustion reaction is really just a special case of a double of a double replacement reaction. And when I say hydrocarbon here, that could be CH4. It's got carbon and hydrogen in it. It's a hydrocarbon. Hydrocarbons are, you know, anything octane, hexane, it's a whole family of carbons and hydrogens in different arrangements. And so gasoline is a hydrocarbon, and if you burn it in the presence of oxygen, you're going to get a CO2 emissions and liquid water. In fact, if you've ever pulled up behind a car and you've seen something dripping out of the tailpipe, that is actually water, and it is a byproduct of the combustion process. Yep. So that's just an interesting fact for you to know. Okay, one other thing that I kind of want to clear up is I will use, and here I use the word replacement, single replacement, double replacement reactions. I will also sometimes use the word displacement. So there's single displacement, double displacement reaction. One displaces the other, one replaces the other. It's those, I use those terms interchangeably and synonymously. They mean the exact same thing. It's just, you know, one, sometimes I have a preference for that. Other teachers have a preference for the other word. Okay. That's really my presentation on classification. The only other thing that I would want to just reinforce, and I talked about this a little bit at the beginning, was why it's so important. Why it's so important to be able to classify. So on your final exam, the boss told me I couldn't give a multiple choice test. I had to give an open response test. So tomorrow I'm going to be posting a study guide for the final exam, and you're basically going to have to predict the products of a chemical reaction and write the reaction equation properly. So what that means is that, first of all, let me get to my point on why it's so important to classify. Say that I told you I had elemental solid iron, a piece of solid iron, like say a nail, okay? And I put that in the presence of oxygen gas. What do you think would happen? Just anybody shout out. What do you think is going to happen if after a while, if I have a nail just sitting around in the air for a long time?
Rust.
Rust, exactly. Yeah. You guys have seen it. You have practical experience with that. And so if I was to, rust is actually a compound. What do you think it's a compound of?
Iron and
oxygen. It's iron oxide, right? All right, so you know it's going to be Fe, and you know it's going to be O. And then the only thing left to do here is to make sure that you have the right subscripts. Let's see, if this was oxygen and it had a -2 oxidation number, this would have to actually be like, I don't know, is there an iron 1, iron 2? I'd have to look at my special ions. This if I wrote it like this with no subscript, then it would have to be iron 2 oxide. Because the 2 would indicate that the iron had a +2 oxidation number, and it would match nicely with the oxygen, which would have a -2 oxidation number. So iron and oxygen combine to form iron 2 oxide. And then the only thing left to do is to balance these. They are out of balance right now because this side of the equation has 2 oxygen, and this only has 1. So I could put a 2 right here and a 2 right here. Because if I put a 2 right here to get 2 oxygens, I'd be throwing the iron off, but I can easily fix that by putting a 2 in front of the iron. So I just did an example final exam problem.